Okay, everybody, welcome back. So let me get started today. So the goal for today is to take the intuition we started with using graph search in discrete versions of the problem, and to sort of introduce that dynamic programming framework as a way to solve our control problems. But I would like to extend it today to the continuous time, continuous state, and continuous action case, right? We actually discretized all three last time. So let me just, for context, remind you we spent some time with one of the few systems that we can solve optimally, which was our double integrator, right? Which was our unit mass on ice, right? Unit mass brick on ice, right? We talked about the minimum time problem. Right? So apply some force, given your force limits, that gets you to the origin in minimum time. And we found the bang-bang control. Which had these critical paths, right? There was some trajectory that was this quadratic form that if I started in these initial conditions and applied maximal braking, this is Q versus Q dot. If I started on this initial condition and applied maximal braking, I would come screaming to a stop right at the origin. There was the same curve for the opposite direction, right? And we had our optimal policy was roughly decelerate as much as possible over here and accelerate as much as possible over here. And that was great because that was one of the very few times in this class and in life that you'll be able to solve a dynamical system and with a cost function and get the optimal solution out in closed form. Right? So nice to do, but don't get used to it, sadly. Okay. There was more hope, though, in maybe getting these answers numerically, right? So we also talked about the numerical version of that. We used value iteration, a form of graph search. Right, where last time we actually we took that same phase portrait and just said, okay, well, what if we had a graph sitting on top of that phase portrait, right? We'll approximate the dynamics as, we discretized state by turning this continuous state space into a handful of discrete nodes in a graph. We discretized actions by saying, okay, when I'm in any one of those states, there's actually only a short, finite list of actions I could take. And I pretended they landed magically in my other bins. And I discretized time, right? Because actually the continuous system takes time to get anywhere, so we had some discrete time approximation. So given all that, we ended up with this describing the dynamics like this. Well, you know what? Let me start on the next board. Given all that, we had pretty beautiful numerical results, I'd say. So today I want to get back to continuous everything. Time, continuous state, continuous action. And think about what that means for the algorithms and what that means for the analytical results, okay? So maybe I can do it like this. Okay, so in discrete time, we wrote the dynamical system in discrete everything. Like that, right? Where I used S instead of X to remind you that that's a discrete finite set. N instead of T and A instead of U, right? Constant reminders of the discrete nature of that. In continuous time and state and action, we were writing it like this, and we want to get back to that today. In discrete time, we formulated the goal for control as we're going to minimize over all A, over an entire trajectory of controls, possibly to time equals infinity. In fact, let's just say time equals to infinity. An additive cost. That was the one that worked well with our graph search algorithm. So the corresponding thing we'll write today is we'd like to minimize U for all time over some integral cost. And the great thing was, if we called this thing the cost that you'd get by taking the optimal actions over time, if we called this J star of, let's say, S0, we defined that as our cost to go, then the magic that powered our algorithms last time was that we could write down that thing recursively, that for all S, I could write it down as minimizing one step right? So that was the same as taking the first step, which cost me G, plus the cost to go of running from being in that state, right? Where J is the cost to go. And it's really, really important. So that was actually, that's sort of two things. For us, last time, we used that as an algorithm. We said if we started with some estimate J, that it was even just random, because in the finite space we could just represent this as a vector. We said if we started with some guess J and just applied this as an algorithm where we had J hat on the next step was, using J hat of the previous step, then we had this magical property that this thing would actually converge to J star. So that was an algorithm, and that's how we used it last time. But there's something more, right? This is actually, it's more than just an algorithm. This is a condition for optimality. This is a theorem, right? This says, even if you don't have a computer around, if you think you've got an optimal controller, right? And you're pretty happy with it, and you want to somehow convince me that you have an optimal controller, then a sufficient thing to do would be to show me that if I plugged in my optimal controller here, and if you can produce some j, some function j, in this case it's a vector, if you give me some function j which satisfies this equation, and the controller you're trying to prove is optimal is the one that minimizes this, right? The controller you can always extract is the argument over a of that, right? So it's the thing that minimizes that. If that's true, then you've numerical method or not, you can convince me that your controller is optimal, okay? And that's how we're going to start in the continuous time. So it turns out there's an exact analogy to this equation in continuous time. It looks a little different, but it's the exact same thing, okay? And that equation in continuous time looks like this. Once again, j is the cost to go. I'll put the star in to make sure you know it's optimal. Okay. And this is again, this is now more famously known as the Hamilton-Jacobi-Bellman equation. Here it's a partial differential equation. So I'll just write partial differential equation. So when you see this equation, we're going to make sure we understand it in some deep way by the end of the lecture. But the first thing I want you to see when you see this equation is that it's exactly this equation. It's just with the sort of the continuous time version of that. The same way this is sort of the natural thing you'd write down for this, taking it to continuous time and continuous state. This is the natural extension of that. So let me try to make sure that you see that with an extremely informal derivation. I feel bad because so there's a great book which I cite in the notes by Bert Sekas, who's in the department, and I'd say it's a pretty rigorous book, and he says things like, here's an informal derivation, and then that's pretty formal compared to what I'm going to write down, so I have to somehow say mine are extremely informal, or just like casual, or back of the envelope, or something like that. But otherwise, I just feel silly. It's all relative. All right, so how do we get from there to there? All right, well, the first thing is let's just take care of that time issue. So, roughly what we're doing to compare a continuous time thing to a discrete time thing, we're taking some finite difference approximation. So, you could think about it if I were to numerically integrate, my continuous time system, I might write down something like this, right? This would be sort of an Euler integration where I've and that's more and more valid as the limit as dt goes to 0, right? But that's an approximation, okay? So let's sort of do the same thing for j, okay? So if I want to approximate what j is going to look like after one step, right? Then what's that going to look like if I've got this thing defined over some continuous space? Well, it's going to look about like jxn plus dt times partial j partial t evaluated at xn, right? Same idea. And what does the time derivative of j look like? Well, in this case, its only dependence on time is through x. So that looks like partial j partial x times x dot, right? But we know what x dot is. It's f of x u, right? So that's where that thing's popping out from. So if I write down that exact same equation, right, but now use this as an approximation, then I could say, you know, I'd like for all x, j star of x is minimizer over u of my one-step cost. But now it's the one-step cost over some interval, right? So I'm thinking about an approximation where j of x is going to be, you know, one-step cost for a little bit for a dt amount, and then the rest of time here. So this is, you know, roughly, this is my rough approximation for the integral of that, plus j of x n plus 1, which is now this whole thing. Get rid of the ends. I don't need those. Yeah? I don't want to spend too much time on the derivation, but I just want to make sure you guys see this is exactly the same thing. Okay? And then I missed a couple stars. And then that's basically it, right? So it turns out since j, if I'm going to say I want to minimize this whole thing over u, if j doesn't depend on u and it comes in like additively, then I can just take that outside. And so I can actually even just cross it out. Zero? Yeah. And then sort of the same thing, if I could actually just as well write it as min over u now of g xu plus partial j partial x f of xu, and take my dt and just put it on the outside. I could do the minimization beforehand, and since the dt doesn't depend on u, I can pull that outside. And since that depended on 0, I can actually just take the limit as dt goes to 0, get rid of my dt. And that's my Bellman equation, okay? So seeing the steps is good, I think, just to sort of exercise it. But really what I want you to see is just that this is the continuum limit of this as my dt goes to 0. Yeah? Okay, I want to think about that though. I don't want that to just be a bunch of symbols on the board. I want that to be something we sort of think a lot about. Okay, so the first statement here is actually it's not an algorithm yet, because we're going to have questions about how do we represent. Now we have a continuous function j, not just a function that's defined at some discrete states or on a graph. but actually some continuous function over x that we're going to have to try to solve for. And that's a harder thing to do. So it doesn't quite give us an algorithm yet. And the other thing that's hard is that now we have to do this minimization over some continuous u, right? The nice thing about this equation, my minimization over a, if a is a finite set, I know how to do the minimization. I can just try every one and take the smallest, whatever the smallest thing is, right? But now I have a minimum over some continuous u. How am I going to do that? That can be arbitrarily hard. If you throw some ugly complex function in here of u, then that can be really ugly really fast. So it's not an algorithm yet, but what it is right now is actually a sufficiency theorem. It's in these other books, but there's something called the sufficiency theorem. The Hamilton-Jacobi Thälmann sufficiency theorem. It's written carefully in the notes. Let me just state it so you don't have to write it all out. If you have a controller that you'd like to show me is optimal, right? Then you need in order to convince me that it's optimal, you need to produce the cost to go function j. That cost to go function, in order for this equation to be meaningful, should be differentiable everywhere. Okay? And it should be that the controller you're trying to convince me is the minimizer of this, given that j. And that whole thing had better satisfy this for all x. Okay? If you've accomplished all these things, then you've convinced me that then that's a sufficient condition for optimality. It's actually not a necessary condition for optimality. Yeah?
Is there any condition for j that doesn't need to be causing it to be quadratic?
No, in general it does not. In general it is not, right? In general it is not. You could say, so for accumulated cost, it's only going to satisfy these equations if it's positive, There's things like that, but certainly not quadratic. Yeah?
Can you say anything if you discover for some controller you have that's close to zero, say like less than a certain epsilon or something like it's kind of good, or is that?
That's subtle. So there are places where you can definitely do that. In this equation, it's harder to do that. It's hard to bound the errors. That's a good question. That's an active topic. But you can have places where your gradient condition is close, is almost zero, but you could still blow up in total cost to go and be arbitrarily bad, I think. You hope that doesn't happen, and that a lot of the numerical algorithms are based on assuming that doesn't happen, but that is a subtle argument. Yeah.
Just to make sure that your j is any cost to go from one location to another, whatever that may be. So.
Well, no. So this is a specific thing. So it's a function of my initial state. I guess I wrote it most carefully right here, right? So S0, and from 0 to infinity in this particular case I've written. There's every permutation you want of this. If you want to do it for a finite time, if you want to have cost that gets discounted over time, there's all kinds of different versions. But just writing in the non-discounted infinite horizon case, this says if I start at this particular state at time 0 and I accumulate cost for the rest of time, what is my cost to go, right? That again is only well defined, just like we talked about last time. That's only well defined if you have a way for your system to get that to 0, right? Otherwise, this sum is going to add up to something infinite. Cool. Okay. So let's do that. Let me exercise this with another example. Okay. So let's take our friend, the double integrator. This time I'll leave u unbounded, but I'll make my cost function be something like this. Okay, so this is it was the other example I ran numerically the other day, where instead of having u be strictly limited, I'm going to just encourage u to be small by having it in my cost function, penalizing the use of force. Okay, and my claim is that I know the optimal controller for this. Okay, it's that's my claim, that that's optimal. All right. Let me try to convince you that that's true. Okay, so I'm going to try to convince you that that's true by producing this function, right? Okay, now, right now you should be thinking, where the hell did that come from, right? But that's okay. I don't have to justify it. I just have to tell you that I have to produce this function. And if these things satisfy the Bellman equation, then you've got to believe me. There's a theorem, right? So you got to believe that that's an optimal controller, right? And I want to say it this way. It sounds a little goofy. You know, a lot of times we want that thing to be constructive and to produce the controller. But really, what it is a sufficiency theorem saying that if you have a controller in hand, you can show that it's optimal. Okay. So let's just exercise our machinery a little bit to make sure we understand this stuff. So how do we take this is a scalar equation in multiple variables, right, in two variables. So it's got sort of two partial derivatives. Oops, I missed a squared. That's important. Yeah. Okay, so, 2 squared 3 is q plus 2q dot is my one derivative. My other derivative, it's basically the same thing. Okay, so I'll write it here. So the equation I need to start dealing with is I'm going to take a min over u of my cost function. Plus partial j partial x f of x. I'll write that in two parts. Let me write that, expand it out. That's the partial j partial q times q dot, right? To make sure you're comfortable with why I did that, right? So this thing is a second order system. Its total time, its total partial j partial t has got both of those elements in it. Okay, if I stick this in, and we don't have to necessarily do it, but just save myself some writing. But if I pop this in, then I've got just a big equation that looks kind of scary. It's got q's and q dots flying all over, right? But it's actually a pretty simple function of u. That was what's key, right? So in particular, it's u squared plus something that doesn't depend on u times u. So it's a quadratic form in u. And because this is just u squared, so it can only look like it's a parabola, right? U squared looks like that. If I add a linear term to it, I can put the parabola on, on the line or whatever, but it's still a parabola. And since this is just, it's a parabola pointing up because that's a positive number. So it's a convex function. okay, basically. So it's going to be some sort of parabola pointing up, possibly slanted a little bit, but still, it's a parabola pointing up. Which means taking the minimum over that parabola is pretty easy, right? I just have to look for the bottom of that parabola. It happens to be the place where the gradient of that function goes to 0, right? I know that that only happens in one place. And I can find it easily. Right, so if I take the gradient of this whole thing with respect to u, and I'll just sort of put the brackets as that whole thing right there, the gradient with respect to u equals 0 is going to be my condition, the u which makes that true is going to be the minimum of that function. Yeah? And every q and q dot I put in, it's going to have a different minimum, but I can solve for the optimizing u, the best u, by looking for the minimum of that function. Okay? So what's the minimum of this? The derivative of this thing with respect to u is just 2 times u from this plus this thing, partial j partial q dot, which is that. So the minimizing u, which is 2u plus 2 square root of 3q. So the u that minimizes that thing is going to be, since that has to equal 0, is going to be negative square root of 3q minus q dot. Which is not quite what I wrote before.
Q dot minus q.
Yeah, it's q dot minus q, but where did I?
It's the...
Oh, I just wrote this one backwards, that's why. Yeah, good, thank you. Thank you. Okay, and guess what? If I pop this back in to here, everybody's good, yeah? If I pop that one back into here, then that whole everything cancels out beautifully and I get 0. Yeah? Okay, so this is just an example of the sufficiency theorem at work. I produced a u, it's kind of a funny looking u. I produced a j. I went through the checks. Everything was continuously defined everywhere. I could take those. It said it met all my conditions. Therefore, you have to believe me now. That is the optimal controller for this particular double integrator with this cost function. Okay, so that's the way that machinery works. It happens, there's a couple things to notice about it, right? So this thing happens to be linear in the state, right? So I could have written this as just a linear function with constant coefficients of the state, right? That j star happens to be a quadratic form right? So we'll see more of that in a minute. Okay, the other problem we studied for the double integrator was the minimum time problem, right? So I could put in the minimum time cost instead. I could put in my u limits. Suddenly then my minimum over u would be a little bit different, right? And it's a good exercise to do. But this would somehow go away. I would still have the linear term in u here. And so now the minimum over u is either going to be, if It depends only on the coefficient here. I'm sorry to say this fast. If it's not helpful, it's okay. I'm just trying to connect the dots for the people who are comfortable here. But roughly, the minimizing over u is still pretty easy in the case of no cost here but bounded u. It just depends on the sign of this term, and that'll either push it to one limit or the other limit, right? If that's a positive number, then the best thing to do if I'm minimizing is to be at negative u equals -1. And if it's a negative coefficient, then I should be at the other rail if I want to make that number as small as possible. Okay? If you check the gradient conditions for that cost to go function for the minimum time, everything checks. It's pretty compelling that that's probably that the thing I showed you before is probably optimal, but it doesn't actually quite meet all the conditions for the sufficiency theorem because partial j partial x is not is continuous but not smooth. So there's a discontinuity that goes through the solution. So it doesn't actually satisfy all the technical conditions for the theorem, but it turns out, it pretty much almost works. It's not quite the perfect example. Okay, so that's how the sufficiency theorem works. That's an exercise with the sufficiency theorem. Let's see if we can, start thinking of it as an algorithm more. Let's use it more constructively. Instead of just pulling the rabbit out of the hat, let's see if we can start, I don't know, finding the rabbits. That sounds stupid. But right, so the discrete version gave us this algorithm, this great thing. We just said, we have an estimate of j, for every s, and we just search over all possible a's. With our original estimate, it had this magical property. Okay? So again, there's a couple things standing in the way from us using this as an algorithm for the continuous thing. First of all, where j we could before write down as just a vector of numbers at each of the nodes, we can't do that anymore. Now j is a function, a continuous function. So we're going to have to find, to make an algorithm, we're going to have to find some finite parameterization of that function j. And the second one is doing the minimization over now a continuous u. So let's see if we can start making progress on that. Let's see if we can attack this optimization over continuous u. In general, it really can be arbitrarily hard. But there's some really relevant, important special cases where it's pretty easy. Okay, and it's pretty general. So there's hope. Okay, so for starters, I told you that most of the systems we're going to see in the class actually have the additional structure of being control affine, right? And so that's going to make this part easier, even just linear in U again, right? So then we just have to decide what we're going to allow for cost functions, right? If you give me the world's choice in terms of cost functions, then it's going to be, again, arbitrarily hard. But let's just restrict ourselves to cost functions of the form where R is some positive so this is my shorthand for positive definite and symmetric matrix, right? So this is actually still pretty powerful in general. You can put a lot of cost functions in. You can tell me, have arbitrary dependence on the state. The costs at different states can be arbitrarily different, right? But I'm going to say let's just restrict ourselves for the moment to places where I'm okay with just penalizing you in a quadratic way. The more you use, the more I'm going to penalize you, right? And we want R to be positive so that number is that thing is going to be just like we did in the last problem. We're going to assume that the function as a function of u is going to be a convex function. That turns out to be a really rich, important, big class of systems. All the manipulator equations fit into this form, right? And a lot of cost functions that people would be happy with or fit into that form. You don't have to have that. If you had bounded u, another solution is to have bounded u and no cost here, or linear cost here. That would be fine, too. There's a bunch of places where you can solve it. This is just the one that matches my last example, and it's particularly useful. Okay, so so in this case now we can solve we can do exactly the same thing we did last time, but to do it in the more general form for any control affine system with quadratic cost in u. And we can solve away that minimizing over u. We don't even have to. It's actually better than doing a numerical search, right? In the discrete time thing, I had to actually evaluate my dynamics for every possible action and take the smallest one. This time I've got a closed form solution, right? I know that the best u I can take is the one that minimizes that whole thing. Again, right? And the math is going to be almost identical, right? So it's going to be now 2 u transpose r. If you haven't done a lot of gradients of vectors, then these might look a little funky at first, but as soon as you do a couple of them, you'll get used to it. I always use the notation that this is a scalar, right? That the thing inside the parentheses is a scalar, and so the gradient with respect of a scalar with respect to a vector is going to be a row vector, right? And this is a row vector, right? Okay. Plus whatever's left on the other side, which is now going to be partial j f2 of x, right? That's the whole thing transpose. So my optimal controller for a pretty general set of things, once you tell me j, I can just read off the optimal controller. It's going to be negative, I'll solve this, negative 1/2 r inverse f2 transpose of x partial j partial x transpose. So for a pretty broad class of systems, we can actually just solve away the u. Now I want you to think about this. I want you to take a second and think about what this is asking you to do, what the best controller is to do. And this is a pretty general setting, right? J is my cost to go, right? J is the cost I expect to achieve given I'm in some state. So partial j partial x tells me if I'm in, at any given state, partial j partial x tells me where the cost to go is going up. This is telling me where it's going to, with the minus sign, it's going to tell me where it's going down, right? So this tells me the direction of steepest descent from my current state in the cost to go, right? Now that's a vector in state space. Somehow I have to map it to the input space. That's what F2 does, right? That maps me to the input space. And then I've got something on the front which modulates me relative to how important, how expensive each cost is. So this thing sort of adds the relative weighting. Right? So if I said it's really, really expensive to use actuator 1, but not so expensive to use actuator 2, then this is what's going to bias me towards actuator 1, or sorry, actuator 2, right? So the basic idea in optimal control is if I can find my my cost to go, then my goal in life should be to run down that cost to go as fast as possible, right? And really the hard thing is finding that cost to go for whatever problem you have. For a lot of problems we care about, once you have the cost to go, you can really just solve and write out the best thing to do relative to that cost to go. Yeah, sure.
Is the F2 transpose or inverse?
These are transposes.
And so the last one there should also be?
Whoa, good catch. No, very good. I wrote an inverse there, and then transpose there. That is our inverse. Yes. Okay, so now what we have on our the problem we have to solve now is to somehow solve this partial differential equation, but we got rid of the min, and life is going to be better because of that, right? Okay, so I'll write it like this. U star transpose R U star plus okay, now that's far from easy, but it's better. Now we're in the land. This is just a partial differential equation, and we can basically bring to bear all the tools people have from the partial differential equation community to try to find a J that satisfies this partial differential equation, right? Now, unfortunately, we know it's potentially tough. Even in our minimum time example, J was had a discontinuity. It was continuous but not smooth, right? It had a notch in it. So that could potentially be a hard thing for numerical methods. But there's a whole world of people that know how to put a mesh over my space X and try to do finite element type algorithms to try to solve for that. Okay. The particular algorithm that I implemented for the example, the value iteration example, is you could think of it as a one version of that. But there's a world of versions for that. And there's, I think, really clever things to do. The land of PDEs is probably most advanced in people who put meshes over two-dimensional space and three-dimensional space. And we have a harder problem here because X can be arbitrary dimensions. You have to somehow mesh n-dimensional space. So the tools that people have done sophisticated things on are more limited than what you find if you look at fluid dynamics or finite or structural mechanics and things like this. But still, there's lots of good tools that exist there. Just find a J that satisfies that. There's a few really, really, really important cases, though, of this where we can do better, and we can actually solve this away completely, right? One of them might be familiar to you. Let me just make sure you connect the dots to that, given the equations I just wrote, right? So the extremely important special case is for linear systems, right? If I have not only control affine, but actually linear dynamics. And my cost function is quadratic in both X and U. I could even have some cross terms in there, that's no problem. Then I can solve this away exactly without even, well, it still requires numerical methods, but there's very good mature numerical methods that are going to give me numerical tolerance to solve that. All right, so this is the linear quadratic regulator. Problem, it's LQR, almost certainly the most important result in optimal control and probably in modern control. I don't. It's fantastically powerful. Okay, so how does that play out? Well, the magic that makes this problem solvable when the system is linear and the cost is quadratic is that someone that came before us who's much smarter than us possibly, I'll speak for myself only, much smarter than me, figured out that all of the cost functions like this have a cost to go that's quadratic, right? So they said, well, you actually it's enough to search for J of X that is some quadratic form. Okay, symmetric positive definite. So let's just assume this right now or guess this. And then everything becomes happy and good, right? So then I'm left with much more manageable equations which say that I've got, well, first of all, we can write the optimal controller down, right? So partial J partial X is now going to be 2X transpose S. U star, certainly this is control affine, so the result I gave a minute ago will work. Partial S partial X now, so it's just S X. which again you should think of as go downhill as fast as possible in my input coordinates scaled by the cost. Yeah. And if I pop that back into the equation, I get some big, scary looking matrix equation. But it's all quadratic in S. That's just how the matrix equations go through. I mean, it's a good exercise to go through and see that, but I don't want to, I mean, that's just falls out. That's exactly that equation with these things put back in. Now it's suddenly, because this has to hold for all x, turns out you can just write this as a matrix equation, that the matrix has to satisfy these things. Again, don't bother writing down all the details if you don't need to write down all the details, but I want you to think about the implications here. Okay, so this is the very famous algebraic Riccati equation. Also known as ARE. And it's still a hard thing to find. You have to solve and find something that satisfies this plus our initial assumptions that S equals S transpose greater than 0. So all you have to do is find that matrix S which satisfies those two equations. That's still hard. There's not a closed form solution. It's somehow quadratic in S in this matrix sense, but there are very good numerical methods for doing it. Okay, so you can call char in MATLAB, and it'll give it these pieces, and it'll spit out an S and solve it with a numerical algorithm. Okay, so it's not quite a closed form solution, but it's the best type of numerical solution, one that you can pretty much guarantee. You can give big big systems of equations that'll come out with S reliably to some reasonable numerical accuracy. Okay, and that's the case where it's a matrix equation which represents the solution to that partial differential equation. Okay. It's a quadratic form, so what's known about this is that there is a unique positive definite solution. So only one that satisfies that, to that Riccati equation. And you can find all of this, by calling LQR in MATLAB, right? You just pass in the dynamics, x dot equals ax plus bu, and the cost, q and r. It'll spit out my controller and my cost to go function. Right? They even use the same letters. All right, so let's make sure we understand that. How many people have used LQR before? Yeah. So what does LQR look like for the problem I gave you earlier? What are A, B, Q, and R? Right, so that original problem where I pulled the rabbit out of the hat and I used the square root of 3 and everything like that, well, that was just LQR, right? That's where I got the square root of 3. Right, so when I had Q double dot equals U, right, so what's A and B? What's A? If I write this as say it again. I can't quite hear what you're saying.
Partial on the first state.
It's true, but you can give me the actual numbers. 0, 1, 0, 0. Perfect. And B? Right? And then I had my cost function was so Q was just the identity matrix, and R was 1, right? So if I pop that into MATLAB, and put it to work, then my answers here are, you know, my optimal controller is u equals negative kx, right? Which in this case was negative q minus square root of 3q dot. And my cost to go was just that thing that I wrote down before, too. Right? So all's right with the world. Yeah?
Sorry, where did you say that u equals negative kx? Up there it was inverse law, and you transpose that.
Yep. That's absolutely still true. But since this is a constant matrix, this is a constant matrix, this is a constant matrix, we just often summarize it by just outputting that constant matrix and calling it k. Right? So this thing is k. So that's super helpful to think that this is the optimal control. It's maybe surprising, but the optimal control is actually just a linear function of the state. Okay, so if I do the same thing we did last time, then I want you to think about this again. So this is the running the value iteration for the minimum for the LQR cost. I want you to watch how it starts. Okay, it starts off sort of it's a quadratic form. The cost to go in particular. Watch the bottom graph is the cost to go, right? Starts off with just a quadratic form, sort of. It happens to be the bowl that looks like the identity bowl. Okay, so you can think about what the value iteration is doing as taking and starting with the one-step cost right? What the value iteration roughly does after one step, if I initialized everything, iteration, if I initialized everything, my initial guess to 0, then after one step, I just have my estimate for the cost to go starts like this, It's my one-step cost, right? And it goes, but it looks like this, right? After one step. And then as the algorithm converges, it goes to the final cost to go, which is the long term, right? So the same way in the grid world, how we watch the cost spread from or the reward in that case, the spread from the goal backwards over the entire map, right? Going around the obstacles. This one, it starts off with the cost being Q, which in our example here was the identity matrix. So it had this nice simple quadratic form, and it warps it to take into account the dynamics of the task as it thinks about the long-term dynamics, right? Now, why does it warp it in that direction? Why is it sort of, what is this saying, right? So the hotter colors, the yellow colors are higher cost. I forgot the color bar in this plot. So why is it better to be, or where is it better to be in the plot, in the quadratic bowl? Lower cost to go, right? It's better to be, to the left of the origin, going that way, right? Going towards the goal, than it is to be, to the left of the origin going this way. Right? That's no good, right? That's only encoded by the dynamics, not from the cost, right? But the algorithm sort of warps the system to find that, right? And then, the best thing to do given this cost function is to go downhill on the cost as fast as possible, right? And in fact, so this is a linear function. It's sliced, and it's the value iteration, since I had to search over a finite number of actions to write my numerical algorithm. In this particular case, it's saturated. So what you're seeing here is sort of the linear function that wants to be slanted like that, but got saturated. Okay? So what it's trying to do is run down the cost function as fast as possible. It can't quite do that. It's being modulated to go downhill where it can actually go, and it's being penalized by R, right? So the linear function looks a lot like this partial j partial x, and it's modulated a little bit by the relative costs. Yeah? Okay, so sorry for a lot of symbols, but let's step back for a second and think about what happened, in all those equations I ended up writing today, right? In the in the discrete time, we had a very simple algorithm, which was just graph search. But you should think about it as more than an algorithm. You should think about it as an optimality conditions, right? In the continuous time case, in some ways, you'd think everything got worse because I can't now somehow just search easily over A. I somehow have to represent this as this J as a function. But there are a few cases where it actually got easier, right? So by virtue of having the same equation be an optimization over the continuous U, there's some cases where I can exploit that and do better sort of than value iteration, because I can solve this away in closed form. No numerical search necessary, right? The other hard thing was this representation of J, and there's in a few magical instances we can actually, again, solve the partial differential equation that's left in closed form, okay? But if not, then we start throwing our numerical methods to approximate, to find some J for which this gradient condition is satisfied for all x. And we can do that with iterative algorithms, okay? The problem is if, most of those iterative algorithms either require making a mesh over the space X, and therefore are limited in the size of the problem you can handle, the number of dimensions that you can mesh reliably. That's one sort of failure mode. The other failure mode is that if you use, so if in the machine learning community, people try to solve these problems a lot. It's kind of funny that there's there's at least two worlds that try to solve these problems. One of them is sort of in the controls community, and they call it optimal control, right? And almost always, the objective is to minimize cost, right? And then in the machine learning world, it's called reinforcement learning, and you try to maximize reward. I don't know if that says something about the type of people that gravitate to those different communities, but they're solving exactly the same problem, and they never talk to each other. It's really annoying. Okay. So the optimal control people have numerical methods for PDEs that work on this. The reinforcement learning people say, well, this is a function in some high dimensional space, so I'll use my tools for machine learning to do function approximation, and which I'm not going to go into. I decided to not spend as much time talking about today. There's a few things about it in the notes, but you can use general tools for function approximation and try to find solutions within a function approximator to satisfy this equation. And those tend to scale to much more complicated problems, but have absolutely no guarantees that they're going to work. So you end up with algorithms that will converge to something, but you have no idea if they're going to be numerically close to the optimal solution or what. So there's some occasional remarkable stories of people using reinforcement learning to find J, and it seems to work, and suddenly, you can play backgammon better than the grandmaster or whatever the problem of the day was. But it's not a sort of something that you can just trust will converge in every case. The few cases where we can solve it, one of the most notable is when the system's linear and the cost function is quadratic. That's LQR. We're going to use that a lot in its various forms in the class. But let me just end by showing you that it's a very powerful general tool. So for instance, what we'll do next time is we start looking at the more complicated underactuated systems. You can just, for instance, take the dynamics of a quadrotor, okay? You linearize them around the top, so you make an approximation as a linear system. You call LQR in MATLAB, you run the simulator, and you can start balancing a quadrotor instantly. So this is the kind of tool that, in fact, I could have shown the same thing for, sorry, probably loading Simulink in the background the first time. First time always slow. Right, I can show the same videos for Atlas balancing, our humanoid balancing if the feet stay on the ground. You can basically just linearize the dynamics, and wow, it's really slow. Is it not playing? Well, it'll balance in a second. Right? Even a humanoid robot with huge complexity, you can still linearize the dynamics, and for some small set of states around the linearization, it'll balance with LQR. So it's a hugely powerful tool. That'll get going at some point. Okay, any questions? Yeah?
So is there kind of like an assumption that you don't start too far away from where you want to?
Exactly. So what we're going to talk about next time is, we're going to start talking about underactuated systems like double pendulum, triple pendulum that swing up and balance, and stuff like that. We'll talk about first the nonlinear control approach to it, and then we'll talk about the balancing at the top. And we'll talk about what linearization means for the nonlinear system and the assumptions that go with it. We'll even give you, in a couple lectures, very good tools for understanding when you're close enough that the linearization works and when the nonlinear system comes up and breaks it. But that takes a couple lectures to get to. Yeah? Yes?
So I know PID is used very widely in industry. Advantages, disadvantages compared to LQR?
This is the the hardest question you can possibly ask a control, modern controls person, right? It's sort of, like, all right, so here, roughly, the history is that, people were doing really good control in 1930 with loop shaping and gain and phase margins. And then in 1950, the theorists got involved and said, everybody's wrong. If you're not doing state space and proving theorems, then you don't know how to do control. And then in the 70s, people realized that, all those theories, actually they make really frail controllers and things break. And so they started talking about robust control and stuff like that. And then there's this sort of thread that's gone along the whole time, which is, well, industry's still doing PID. Everybody who does real systems still uses PID, and I think so PID works really well if you have an actuator. Every time you have an actuator next to a link, and you want to you have a single input, single output system, or you can decouple your system into a bunch of those things. LQR is a PD controller. It doesn't have the integral term. That's one thing that's sort of missing, and it's surprisingly hard to get the integral term back out. I mean, you have to encode model error and other things for it to make sense from an optimality standpoint to get an integral term back in. But you could think of LQR as being a better PD controller, where it has terms that couple between different joints, for instance, whereas a PID would typically be every joint independently. The other thing that's nice is, so if you think about this as a tuning exercise, let's say you wanted to tune in a good controller, for the PID control, or just PD controllers, since that's a more fair comparison, if you change the gains, P and D, you can go back and forth from having a stable system to an unstable system. Okay, so you could change the gain a little bit, your system goes unstable, you change it, whatever. You could think of this as a different way to parameterize the PD gains, where the things you're tuning are now Q and R. And as long as you pick positive Q and positive R, you're always going to get a stable controller out. But they actually describe the same family of closed loop systems. So if nothing else, optimal control gives you a way to parameterize this set of stable PD controllers. I'm embarrassed that it doesn't handle the PID controllers nicely, because I think that is important, and that has to come out of robustness. But for PD, this owns it, and I think it's a more natural way to do it. The only thing that's different, some people have good heuristics for tuning in PD controllers that maybe it's you'd have to have the same good. I think people who use LQR know how to tune Q and R. People who use PD know how to tune P and KD. But I just think LQR is a slight generalization. Yeah. Uh-oh.
I mean, one good counterexample is try doing PID control on a system with a non-minimum phase zero, like a follow car.
Exactly right.
That's
and then that's hard again, right? And partly because of the coupling between the multiple joints, right? I mean, that's exactly right.
that's LQ true.
Where LQR is trivial, exactly.
If you want to add an integrator, can you just add one state that's just accumulated state to your queue, and then your LQR should be PID?
So, okay, yes, you can get something like an integral out of that, but the reason I think for integrators is to capture model error and things like this, right? It's to integrate out long-term errors. So I think to get the integral for the right reason, I think you need to start talking about model errors and robustness. But it's true, you can get something that would have an integral term in it, but I think you'd have to have a reasonable model for that last derivative. That was sorry for the long answer to the short question, but that was a really good question, yeah. Yeah?
So just to be clear, this works for systems where there's a natural linearization, but it won't work for sudden loading of the system, right? If someone came along and kicked Atlas, we wouldn't be able to use a controller of this type to balance it.
So the short answer is, if the system, so let's differentiate between instantaneous impacts or uncertainties versus if you've changed my model, then that's a different, harder question. But if you just sort of knocked me and I have to recover, then the question is sort of how far from the linearization point are you? And we're going to give you a very satisfying answer in a couple lectures on how to compute that. Yeah. If you were to somehow put a constant force on Atlas, then you've effectively changed my model, and then it's a different set of questions. We talk about robustness and to model errors. Okay, great. I'll see you on Thursday. Yeah.